All right, 3.2, we're continuing our discussion of polynomials. In particular, today we're going to be talking about zeros of polynomial functions. So zeros are actually places where it crosses the x-axis. That's what they are. So we're going to be looking at different ways of making those kinds of decisions and discovering those kinds of features. A couple of theorems to start with. The first one's called the remainder theorem. The remainder theorem says that if you have a polynomial, p of x, and you're dividing it by a binomial x minus c, then the remainder is the same thing as evaluating the function p at the point c. And the second one is called the factor theorem. The factor theorem is just a specialized case of the remainder theorem. It says that if in fact this x minus c that you've divided by is a factor, then you get a remainder of 0. That's what factors always mean. That's what they mean for my 7th graders who are working with factors of denominators to add fractions together. That's what they're doing right now. My two 7th graders are. This means it's a factor if you divide it evenly, right? No remainders. So it means the same thing for polynomials. Now, in particular, we've talked about factoring like quadratics, and to some degree, some general, not general, but very specific types of polynomials. But we haven't talked about how to do this in general for any and all types. So that's actually what we're going to be taking a look at next. And it may or may not be something you've seen. Sometimes it'll occur in some algebra classes in high school. Sometimes those topics that kind of get skipped over as well. So this may be something you've absolutely never seen before. What we're going to be using is synthetic division. So just a real quick show of hands. You don't necessarily, I'm not going to put you on the spot and say do it for me, but how many of you have seen synthetic division before? Okay, we're at about half, maybe a little bit more. So synthetic division is a method of doing division where we kind of ignore all the variables. So it makes it a little easier to work with. There's less going on in the problem. The alternative to synthetic division is called long division. You may have done long division with polynomials as well. It's important to sort of make mention of the fact that the synthetic division is only going to be helpful because we're dividing by a binomial. If we were dividing by a binomial, we would not be able to do that. But if you take a look, everything we're working with right in this section is binomials, which is why we're using synthetic division. Okay, so they're going hand in hand for us. This piece that I'm dividing by, if I were to set that equal to 0 and solve, what would I get? Yeah, x is 4. So that value is the value that I need to use for my synthetic division on the outside. So I'm going to put a 4 kind of in a half box, basically, sitting on the outside. And then what I'm going to do is I'm going to put each of the coefficients of each of my variables in a row. So there's an understood coefficient of 1 here, right? There's a coefficient of -3 here, and there's a coefficient of 9. So in a very real sense, we have an x squared column, an x column, and a number column. If we were working with polynomials that are bigger than this, right, like they have x cubed or x to the 4th, it just means you have more columns, all right? And I want to put the coefficients in. So this is a 1, a -3, and a 9. Okay, so is the setup okay? We're going to do this setup several times today. I mean, like at least 3, because on this front page of my notes, I have 3. Oh, no, we're going to do it more than that. We're going to do it a lot. So for a while, I'll write the headers x squared, x number, or something like that. But eventually, I'm going to stop writing them because they'll be natural to you to know that they're going there. So for now, we'll keep them written. So what we do with synthetic division is we actually first bring the first number straight down, 1. Easiest step right there. The second step is to multiply that 1 that's on the bottom now times the 4 on the outside. I get a 4. And then I add down. What's -3 plus 4? 1. And I do the multiplication again. 1 times the 4 on the outside gives me 4. And if I add down, I get 13. This number at the end that I get is the remainder. And according to what we saw in the previous factor theorem, I'll flip back over here, if that remainder had been 0, it would mean that the x minus 4 was actually a factor of the polynomial I was looking at. And it shouldn't surprise you that it's not a factor on this, because if you looked back up at the original one, x squared minus 3x plus 9, if we were to attempt to factor this, there's no way x minus 4 comes out as a factor of that, right? Like, that's ridiculous, because 9 doesn't even divide by 4. But it does tell us a little bit more information, because we actually get the whole remainder, which is a 13. And that's what we were asked to find. Use synthetic division to find the quotient and the remainder. We found the remainder. I'm sorry, I didn't write the quotient yet. The quotient comes from this piece right here. These are now the coefficients of a polynomial that has 1 degree less than I started with. I started with a polynomial that's x squared. So the polynomial I get at the bottom will be x and a number. In particular, this is 1x plus 1, or you could just put x plus 1. So this is my quotient. So those are the two pieces of information I was looking for. So far, so good? There are several types of questions that are actually asking you to do the same operation. So this is one of the types of questions. It gives you a polynomial. It gives you a potential factor. It says do synthetic division, find the quotient, find the remainder. Another very similar type of question to that, or at least it's asking you to do the same thing, is to find f of negative 1 using synthetic division. So while it's true that this f of negative 1 means I could plug the negative 1 in and I get the answer, and you could check to see what that is, that's not what the question's asking you to do. It's asking you to use synthetic division. Okay? So again, over here with the remainder theorem says that finding, in our case, f of 1, or negative 1 it was, f of negative 1 is the same thing as doing synthetic division with the factor x minus that value. The cool thing about it, though, is that it's already solved for x. So right here, when we were given the polynomial that we're dividing by x minus 4, we had to set it equal to 0 and solve it. Over here, it's already done. The negative 1 is the number that goes on the outside of the synthetic division. I don't have to set anything equal. It's simply negative 1 out here. So I have a cubic polynomial, so I've got a column for x cubed, x squared, x, and the number. And you do need a column for every single one, whether or not they are present in your polynomial. It starts with x cubed, and it has to go all the way down to the constant numbered column. So what does it mean when one's missing? Well, it means that there are 0 x's. But I need that placeholder. It's like saying the number 101, right? I need the 0, otherwise the two 1s are not in the right place value to make sense of the number 101, right? You eliminate the 0 and it's 11. And 101 is not the same as 11. You need the 0 placeholder. I need the 0 placeholder here too. Now, all the rest of them are just the coefficients like we did before. So there's an understood 1 here. So I have a 1 in the x cubed column. My x squared is negative 4, and my constant is 8. Are we okay with the setup? Awesome. All right, so we're going to leave a little space for the numbers to go in between. And the first thing is to always bring the first number down. And the second thing is always to multiply. So I take the 1 that's been brought down and I multiply it by the negative 1 on the outside, so I get negative 1. Okay, so if I add down, what do I get here? Negative 5. And if I multiply my negative 5 by negative 1, I get 5, so it goes in the column with a 0. I add down, I get 5. I multiply by my negative 1 on the outside, negative 5. I add down, I get 3. So this 3 at the end is the remainder, right? And while I wasn't asked for it, I could in fact find the quotient as well, right? It's written down there at the bottom. It's going, if I were asked to find it, just for a real quick reminder, I do 1 degree less, so this is the x squared, this is the x's, and this is the number. The quotient would actually be 1x squared, or just x squared, minus 5x plus 5. Okay, I wasn't asked for that, but that's what it would be. Okay, I am asked actually to find f of negative 1. And f of negative 1 is the same thing as asking what's the remainder. So f of negative 1 is the same as the remainder, namely 3. And if you wanted to confirm that, right, with the other skills you know from algebra, you could take negative 1, you could plug it into the equation, in place of all of the x's and confirm that you do in fact get a 3. So this particular problem you can check whether it's even or odd very easily, either using some real basic substitution or even using your calculator with substitution if it gets messier. Any questions on that? Okay, we're going to have another way of asking the same question. Okay, this is one of those problems with terminology in math, is that we have lots of words that mean the same thing sometimes. Y'all know this to be true, right? Lots of symbols sometimes that do the same thing. So this is another question asking you the same thing, or at least asking you to do the same operation. It's asking whether the number -1 is a 0 of this polynomial. So again, one of the things that you know from previous work is, hopefully, or remember this word, is that 0 means the same thing as the x-intercept. In other words, if I plug the -1 in for x, do I get y equals 0 when I'm done? That's what it's asking. But this section is wanting us to do this with synthetic division. That's the whole point, the connections between the two concepts. So we're using the -1 on the outside, and we're doing columns for x cubed, x squared, x, and my constant. And you don't have to write those above them, but if it helps you to keep them straight, then please do. I have 3x cubed, 2x squared, -2 in the x, and then -1 as my constant. Okay, set up okay? All right, this is like the shampoo bottle. It's wash, rinse, repeat. We're just doing the same thing exactly again, right? Okay, so I bring my 3 down. This is the first time I brought something down that's not a 1. It doesn't change anything. It just still gets brought down. And then I take that 3 times the number, in this case it's -1 again, on the outside, and I get -3. If I add down, what do I get? -1. Now what? +1. And then another -1. So it's +1. And what happens in the last placeholder this time? I actually do get a 0. If I get a 0, like I did here, then this answer is yes. And it's yes because the remainder is 0. Okay, so the answer is yes. I'm writing down because the remainder is 0, so that hopefully when you look back at this, you'll remember how we made that decision. And we made that decision based on a theorem that we had called the factor theorem. The factor theorem says that if C is a 0, then we have C as a factor. These are going on, right? They're factoring, it's working out to be 0, have 0 at the end. All those things are connected. So when I get that 0 as my remainder at the end, it really is a 0. That is, the x value of -1 is a 0 of this particular function. And again, if you wanted to confirm that, right, in terms of like a substitution method, you could evaluate this and say, well, what is w of -1? I didn't do it on the last one. Let's just do it on this one so it will remind you how to do it. You would be evaluating with a -1 in for all the x's. You need to be doing each of the steps of multiplication, simplification, and in fact, if we're correct on both pieces, we should end up with the same number here at the end that the remainder was, which was a 0. Okay, so this is kind of like a check step for us at this point on this particular type of problem. Okay, any questions on that one? Okay, so another phrase, is it a factor? So is something a 0, is something a factor? That's the same question. But the difference, of course, that you notice is that it's given to you in a polynomial form, right? It doesn't say, is -1 a 0? It says, is x plus 5 a factor? Well, what does that mean? Well, it means that if I take x plus 5, just like I did on problem number 1, when I had that x minus 4, and I set it equal to 0, that's the number that's in the box on the outside. So I need to take the x plus 5, either in my head or on paper, whatever it takes for you to see what it is, set it equal to 0, and what will x equal? -5. So -5 is the number that's in my box on the outside of my synthetic division. So at this point, I'm going to stop writing column headers. If it helps you to keep them straight, still keep writing the x cubed, x squared, all of that. Anytime you have a missing factor, you have to be careful. This one doesn't have a missing factor, so it's the coefficients that are showing up. I have a 1, an 8, an 11, and a negative 20. Is the setup okay? Great. So we're going to draw our line, and we bring the first number down. Now what? Multiply, and I get negative 5. 8 minus 5? 3. 3 times negative 5? Negative 15. This one's giving me a little bigger numbers than I've worked with on the other one. That's okay. 11 minus 15? Negative 4. Negative 4 plus 5? Negative or positive? Positive this time. 20. Leaving me with 0. So, again, this 0 gives me the answer that yes, x equals negative 5 is a 0, so x plus 5 is a factor. Yes, it works. Now, I have asked questions like this on tests before where it's set up just like this. It asks this question, and then it asks right after you for you to factor something. These problems are related, right? Like, it's not intended for you to go back up to the x cubed plus 8x squared plus 11x minus 20 and somehow try to factor by grouping. That's not what it's asking you to do. Now, that might be a possibility of how to do it. It depends on the problem that's given, but it might not even work with factoring by grouping. But what does work is the fact that at the end here, remember, we have a quotient. Okay? What does that mean? Well, it means that this x minus 5 as a factor means that there is an x minus 5 that comes out. This quotient creates the other piece of the factoring. That's what happened. So in a very real sense, synthetic division, when it ends in a 0 at the end, right, when the remainder is 0, it factors a problem for you. So you had your sort of traditional factoring with trial and error, or the AC method, or maybe slide and divide, right? You had those kind of options. We've had factoring by grouping, and now we have synthetic division as another place where we can actually use to factor, or another method to use to factor. And again, just like on the other things, they don't work for everything, right? If this had not been a 0 at the end, I wouldn't be able to use it. It wouldn't have created the factoring that I need. But because it was a 0, it will work. So what is the quotient that I'm going to write in here based upon this piece over here, the 1, 3, and negative 4? So I have 1x squared, or just x squared, plus 3x minus 4. Is that okay?
I have a question.
Mm-hmm.
So what happened is at the beginning, like in that column, that first column is an x cubed.
It is x cubed. If you take a look at all these that I did on the first two, is that it goes down 1 in degree.
Okay.
And the reason it goes down 1 in degree, Kylie, is because we're dividing by a factor that has an x in it. So this 4 over here is representing the dividing by x minus 4, so I remove a degree every time I do a synthetic division step. Yep. All right, so I have x squared plus 3x minus 4. And what I want to do then is I want to factor what remains. That is, I want to factor this piece that's, still a trinomial. It's got 3 terms to it. So how will x squared plus 3x minus 4 factor? Well, it starts out with x and x. I'm just going to use trial and error because it has a coefficient of 1. The value is negative at the end. That is negative 4, so I need a negative and a positive. Then I need 2 numbers that multiply to 4 and add to 3. So what will it be? Negative 1, positive 4, precisely. Okay, so this is the factor completely part. That's the solution for that. So this is one of the 2 pieces that I was asked for part B. The other thing I was asked to do in part B is I was asked to find all the zeros. Well, one of the zeros I already found in part A. It was x equal 5, right? I already have one of them. The other 2 zeros come from these parts that I just factored to finish the factoring completely. So just like with x minus 5 set equal to 0, I get a 0, x equal 5. Also, on these 2, I can do the same thing. So I have x minus 1 equals 0, and I have x plus 4 equals 0. So
why are we doing x minus 5
because I just wrote it down wrong. I apologize. It's that zooming in and unzooming out. I lose signs. Sometimes numbers too. Thanks for fixing that for me. So it should have said -5 over here. There we go. I think we got it all fixed now. I think that looks good, yeah? Great. Okay. How about my x minus 1 equals 0? What will that give me for x equals? Yep, that's x equal 1. And x plus 4 equals 0? X is -4. And while it doesn't have to be true, it is, I don't want to say most often the case, but it is often at least the case, that if I have a cubic, I will have 3 solutions. At the very least, I can't have more than 3. 3 is the most I can have. Sometimes they duplicate too. I could have 2 of them that match or something like that. But oftentimes I'll have 3 separate ones.
So if they match, you only have to write them once?
Yeah, you would only have to write them once. If you wrote them twice, though, it wouldn't be wrong. Okay, any questions on that? Okay, so those are all really questions asking you to do the same thing with the exception of this last one where I went just a little bit further using stuff we've done before. Okay, the other thing in this section is something that has the phrase fundamental in it. And anytime you see the phrase fundamental in math, it means it's really important. So this is the fundamental theorem of algebra. And you're in algebra. There's a fundamental theorem of calculus. There's a fundamental theorem of counting. There's lots of fundamental theorems. It means it's really important. So the fundamental principle of, or fundamental theorem of algebra says that if you have a polynomial and it's not constant, so you can't have like y equal 5. Y equal 5 is a polynomial, but I need something that's not constant for this to make sense. Okay, so a non-constant polynomial, then your polynomial will have at least 1 0. Now, it may not be real, it might be imaginary, but it has to have at least 1. And the most that it can have, as I mentioned before, is the degree of the polynomial. So when we did an x cubed one, the most it could have is 3. Has to have at least 1, the most it can have is its biggest degree. The rational theorems test tells you how to find the rational theorems that are a part of that. Now remember, rational theorems are things that can be written as fractions. Rational meaning ratio, right? So 1/2 is a ratio, but so is 5, because it's 5 to 1. So rational theorems, talking about any whole numbers, any integers, any fractions, any decimals that you can actually use as a divisor or a portion of your divisor. So it says for a polynomial function p of x with integer coefficients, you do need integer coefficients, all possible rational zeros have the form p over q, where p is a factor of the constant term, the number at the end, and q is a factor of the leading coefficient, okay, the number at the beginning. Now, the possible rational zeros theorem is helpful in general, period. But it is most helpful when you have some kind of a calculating device that allows you to graph. I mean, that's just it. You can do it with other things, but it's most helpful if you have a calculator that has a graph. So we're going to use calculator with graph today. Obviously, if you don't have one for a test, it's not something that you're absolutely going to have. I'll make sure that when I ask my questions, they're asked in a way that don't make it unfair if you don't. But for your homework, you would always have an option, even if you don't have a calculator, because you have your computers, right? And you can actually graph on the computer with different graphing sites as well. So what this is actually telling us for the first question, I don't necessarily need it, is all the ways I could get possible numbers where I have rational zeros. So let's take a look real quick at an example where it's kind of messy. And it's intended to be messy on purpose because I want to show you how it really works with something, with numbers that at the end and the beginning that aren't 1 or 2, something that are a little more complicated. So what this is actually telling you is that these are the values at the end that are p, and these are going to create, this number at the beginning, 8, is going to create my q's. And what I want to do is I want to list all the numbers that divide it. So I'm looking at factors or divisors of these numbers. So we'll start with the number 8. First of all, positive or negative, because you could have positive numbers that divide it or negative numbers that divide it. And you're always going to get the number 1. I'm going to write them out in order, or you can write them out in pairs, right? So like if you want to write 1, make sure you write 8, because 1 times 8 is 8. What's another pair of numbers that multiply to give me 8? 2 and 4. And for this one, that's it. 1, 2, 4, and 8. We're going to do the same thing for the 15 at the end. Again, there's a plus or minus. And it's all the numbers that divide 15, excuse me. So I've got 1 and 15. What else will I have? 3 and 5. And I don't mean for this to look like, hey, there's always going to be 4 numbers that divide, the one at the beginning, the one at the end. That doesn't happen. Sometimes there's nothing. It's just the number 1. That is just it. That's all there is. Sometimes it could be more than that. If you had 12 at one of these locations, you get more than 4 factors. I think you get 6. Okay, so you can get different numbers of factors. And what we're doing is we're going to write out everything that's in P divided by Q form. So as an introductory step for doing this, you might recognize that both of these lists have positives and negatives. I'm only going to list it one time because listing it twice just simply isn't necessary. And I'm going to list all the numbers that go on top and all the numbers that go on bottom. I won't be finished at this point, but it gives me a way to make sure that I don't forget something along the way. So the p-values, the ones at the end, are 1, 3, 5, and 15. The q-values, the ones at the beginning, are 1, 2, 4, and 8. So I know none of this is sort of just piecing together as to what I've really found. I promise I'll come back to that. I just want to show you how you do it first, and then we'll talk about why it works. Okay, so again, we've got the plus or the minus, and what we're going to do is we're going to take each of the individual numerators and divide it by the denominators. So if I have 1 divided by 1, I get 1. 1 divided by 2 is 1/2. 1 divided by 4 is 1/4. And 1 divided by 8 is 1/8. And once I've gone through all that division, I'm done with the number 1 and I'm on to the number 3. 3 divided by 1 is 3. 3 divided by 2 is 3/2. 3 divided by 4 is 3/4. 3 divided by 8 is 3/8. And I'm done with my 3's. We'll move on to my 5. 5 divided by 1, I'm going to run out of space, so I'm going to move down, is 5. 5 divided by 2 is 5/2. By 4 is 5/4. And by 8 is 5/8. Hopefully you're bored. Because it should feel like, I just did it. That's what it should feel like. If you feel so much routine that you feel like, didn't I just do that? And the answer is yes. You're going to do it 4 times because we have 4 numerators. So we did it with the 5, and now we're going to do it with 15. So I have 15 divided by 1, which is 15. 15/2, 15/4, and 15/8. How many of them are there? Okay, there's 16 in here, but there's a plus or minus at the beginning. There are 32 possible rational zeros. So the idea of the possible rational zeros theorem is that it takes something that has unlimited possible zeros. Because you do. You have unlimited, like infinitely many, not possible to ever count, like more than the stars in the sky kind of stuff. Right? More. Infinitely many. And it narrows it down, but let's be real, narrowing it down to 32 is still a lot of numbers. And if you were to have to use either synthetic division or plugging in each one of these numbers, you do not want to plug in 32 numbers to try and figure out which one works. Can I get an amen? Do not want to do that, even if it only took you halfway through it. That's a lot of work. So let me show you how your calculator can come in handy. So if you're looking at this on the video later, you won't be able to see my calculator screen, and you'll just have to follow my prompts verbally on how this is working. So you're going to take, if you have a calculator like this, or if you are using a device on the computer later, and you want to use your actual equation that were given inside of the graphing menu. Okay, so I'm going to put my equation inside of y1. So it's 3x to the third, wasn't it? No, 8, sorry. Thinking of a previous problem. 8x to the third minus 36x squared plus 46 minus 46x minus 15. And depending on how new your calculator is, it might not do this thing where it wraps around. It might just continue along the first line. That's fine. Just going to look at it in a regular like 10 by 10 window. That window is located underneath the zoom button where it says zoom standard. And what we're trying to identify using the rational zeros theorem is where it crosses the x-axis. That's what all these things are. These zeros, these roots, they're places where it crosses the x-axis, namely x-intercepts. And as you look at this one, you can kind of see that it looks like there's 3 separate locations here, right? But because it's so tiny, it's really hard to see. And if you take a look back at your equations that we just did, or not equations, but all those list of points, it could be a lot of those points because they're really tight together, right? 1/2 and 3/15. I can't tell the difference between that and this screen. It's not possible. So it would be helpful for me to look a little bit closer in here. There's a couple of different ways to do that. You can use the zoom feature and you can just zoom in. That's one option. You can use your window feature and minimize the window so it only goes from like 0 to 5. That's fine too. It doesn't really matter which one you use, but you definitely want to zoom in on the Y as well. So if you zoom in like that, you want to do the same thing here. Maybe like -5 to 5 just so that I can see both above and below the x-axis. So it looks something like this. So this calculator rendition of this, I can get the screen to not be so bright. I can't. Oh, I could do it like this though. I want it to be low enough I can point to it. I'll just pretend. Okay. This location right here, the first one, right? It's showing mine is showing hash marks at every unit that's 1. So it looks like it's the number 1/2, doesn't it? That looks pretty realistic. We only need one of them, by the way, if we were actually trying to find this. So once I can identify one of these places where we're like, yeah, it really looks like it's that, that's the one we can actually utilize. Okay, so I'm going to switch back to my iPad screen because this problem didn't ask me to actually find the zeros. It just asked me to list them all. So I've actually done everything I'm supposed to on this particular problem. I just need to move to the next one so I can show you what the next step is when the directions change slightly. Okay, so this one asked me to list all of them. This is the list that we're looking for. And we all recognize that it's 32 numbers. This problem, however, is asking me to actually find the zeros. Okay, so what I'm really wanting is I'm really wanting to try and figure out what are the values that it could be, because there are not infinitely many. According to the rational zeros theorem, there are finitely many, and it's very finite on this one because my numbers are not 15 and 8. They're much nicer. So what are the factors of the number at the front? Well, there's 2 of them. 1's great. And 2's not much worse. There's only 2 of them here. Right? So if I were to list this one out with all my p's over q's, I'd have the plus or the minus. The numbers at the end, the p's, are the 2 and the 1. The numbers at the beginning are the 1. That's not very many numbers. And if I were to do what I did last time and divide each of them by the number on bottom, which is super unexciting because it's 1, I will end up getting that I have 2 divided by 1 is 2. 1 divided by 1 is 1. And I might even want to go ahead and sort of distribute the positive negative through and recognize I have 2 and -2, 1 and -1. And if I really had to test 4 numbers, we would all be okay with that. Especially after I told you 32 would be bad, right? And we agreed. 4 would not be bad numbers to test. But if we could test the right one first and save ourselves 3 other steps, it'd be nice. Agreed? It would. Okay? So this is an example of a problem that I could put on a test. And if you didn't have a calculator, it'd take you a little bit more time, but it wouldn't be ridiculous. All right? It wouldn't. But if you have a calculator, one that you could borrow when you get to that point, it might be helpful. So let's take a look at how we would actually utilize the calculator to eliminate some of the choices of what to test. So my equation is going to be the one that I was given here, which was x cubed minus x squared and plus 2. I'm going to put it back in that standard window, so zoom 6, so I can see where to start looking. And if I only have 4 options, and it says I do, 2, -2, 1, and -1, what does it have to be if I'm looking at this visually, if it exists at all? What does it have to be? Yeah, if there's a rational zero, and there doesn't have to be. Notice over here, and I can't go back because I'm not on my screen for you guys to see it right now, but if you go back in your notes to what we did before, it's telling you that there's a zero that exists, but it does not tell you that it is rational, does it? So there may not be a rational zero that works. If you looked at this graph and it was completely all above the x-axis and it never crossed the x-axis, there's not going to be any rational zeros. I don't care what P over Q gave you as possible options, there's none that are going to work. If there's one that's going to work here, it's going to be -1, right? It's the only one that's going to be possible. So we're going to do synthetic division with that -1 on the outside. So -1 is going to go on the outside, and I'm going to put the coefficients in order. Now notice I do have a missing exponent. So I have 1, -1, 0, because there's no x term, and 2. And if it bothers you to see that, just make it your habit to always write the exponents above, right? X cubed, x squared, x, and your constant. If you need to remind yourself to not miss that 0, whatever it takes. Draw our line, bring down the 1. What's my next number? -1. And then -2. And then 2. And 2. And then -2, which yields 0. It worked. Okay, 0 is what we're looking for at the end for it to actually end up being a factor. So it worked. Now it says find all. Okay, it didn't say find 1. It could say find 1. I mean, that would be fine. It could say find 1, but this one didn't. It said find all. So right now we found one of them, namely we found x equal -1. How do we find the rest? Well, we take this piece right here and we factor it. So this is the values x squared minus 2x plus 2. So if I try trial and error, this would be x and this would be x. The sign at the end says the signs need to match. The sign in the middle says they both need to be negative. And I run into a problem. The only two numbers that multiply to the 2 at the end are 2 and 1, right? But when I put the 2 and the 1 end, what happens? Yeah, like verbally, like written out long ways, it doesn't add up to the -2 in the middle. Shorthand, it just don't work. Right? And it doesn't work because these two and these two, when we multiply those pairs and add them together, don't give me -2x in the middle. So what does that mean? Well, it means that it does not factor. You guys know what to do when you have a quadratic that does not factor. What do? You could complete the square. I don't know anybody that would. I mean, but you could. You could do quadratic formula. That's usually where we go to next, is the quadratic formula. So if I use the quadratic formula here then, x equals -b, so that's negative of -2, and the numbers I'm using are right here, right? This is a, b, and c, 1, -2, and 2. So x equals opposite of -2 plus or minus the square root of -2 squared minus 4 times a is 1 and c is 2 all over 2 times a. Okay, so we're going to get this cleaned up. It's 2 on the outside. I have 4 right here minus 8. All divides by 2. What's 4 minus 8? -4. What happens when I have a negative underneath the radical? I get i's. Okay, so we have that 2. This is now plus or minus 2i, right? Square root of 4 would be 2, so -4 would be would be 2i over 2. And if I were to divide everything by the 2's, I would find that I'm running out of space is what I'm really going to find. I would find 1 plus or minus I. Those are my other two zeros. You can leave it written that way. If you want to write it out so that you list them each separately, it's 1 plus I and 1 minus I. You don't need to list them out separately, but there are, in fact, 3 zeros. And it kind of shouldn't surprise us that the last 2 zeros ended up being imaginary. And here's why. When we looked at our graph, did it ever cross the x-axis again? Nope. And when it doesn't cross the x-axis, it means none of the other answers that show up will be real solutions. They'll be imaginary or complex solutions. So that's why that's happening. Okay, so we're going to do the same process again, but the problem is actually messier with the beginning and easier at the end. Okay? So I wanted you to see lots of things. This is messy at the end because I have to use the quadratic formula, right? I mean, it is. It would be nicer if it factored. We would all be a little bit happier about it. But the beginning part was really nice. There weren't a lot of things to test or to check. Agreed? Yeah. So we're going to flip that around this time. Sometimes they're easy on both ends, but this one's going to actually go the other direction. So as you take a look at this particular equation, you can see, hopefully, why it's messier at the beginning. You see a 15 and a 14, don't you? Not a 1 and a 2. And that's why. So if I were looking at my p's here, I have the same 1, 3, 5, 15 I had on the previous 2 problems ago. Yes, sorry, and I also forgot my plus or minus. Come on. Thank you. Get the letters right. At the end, my p's, there's the plus or minus in that one, would be what? 1, what else? Yep, 2, 7, and 14. Now, I'm not going to write it all out longhand like that. But what I am going to do is to sort of think about it in this condensed form like this. Okay? Because I wasn't asked to write them all out. I mean, I need to know what they are so that when I look at the calculator, I can pick one that makes sense. But I don't have to list every single combination out because I wasn't asked to. So as I list out my p's divided by my q's, and I'm going to actually put them up here so that I can try to save some space. We have all of our constant values, which is 7 and 14. And we have all of our leading coefficient values, which is 1, 3, 5, and 15. So we have numbers like 2/5 and 7/3 and 1/15, right? Numbers on the top divided by numbers on the bottom. So as we look at our calculator, if it looks like it's crossing at about 1/2, we need to look back here and say, but it can't be 1/2 because I don't have a 2 in the denominator. So it must be something really close to 1/2. What other combination looks like it might be a 1/2? Is everybody tracking with me? I mean, I'm not saying it's going to be a 1/2, but you have to use that as a guide because you don't want to test things that are not going to work for sure. Because if it doesn't fit into this category, it's definitely not going to work. All right, so let's utilize our calculator and see if it can help us choose a good value. All right, so we're going to put in 15x cubed minus 37x squared plus 44x minus 14. And we're going to do that same Zoom 6 standard window. I feel like I might have a sign wrong because it definitely crosses. Let me double check. It may not be in this window though. Oh, my 15 got left out. My 5 here. 15x cubed, 37x squared, negative, positive 44x and 14. Okay, let's try again. Here we go. Wow. Kind of really does look like it's about 1/2, doesn't it? Let's zoom in this time. I didn't do it that way before, but you can actually hit the zoom in feature, number 2. And if you just press enter again, it will zoom in right there in the middle. And it really does actually look like 1/2. Probably just remembering from when I taught it a year ago or whatever, 6 months ago. Really looks like 1/2, but I know that I can't test 1/2. It doesn't make any sense. It won't work. So what options do we have that might work? Well, actually, let me just ask that before I move on from the screen. What might work? Maybe 2/3. It's a possibility. Okay. I'm going to jot them down. You guys jot them down too. So we might try 2/3. What else might we try? Maybe 7/15. That's going to be awfully close to 1/2. Anything else that we might try?
2/5.
Maybe 2/5. Those are probably my only options that have a chance. Agreed? And if I had to test all 3 of them, I could. Okay, so this is an example of one that I would not be asking you to do on a test, because you need the calculator to be able to narrow some of this down. Tiffany?
Be able to look at the table.
That's where I'm going.
Okay.
Yes. Okay, so you actually have in your calculator, in this kind anyway, a table function. And that's exactly what I would suggest doing. We would like to know which of those three to try. Because I don't really want to try even three of them if I don't have to, especially because they're all fractions. Okay, I'm going to have to do synthetic division with a fraction on the outside and multiply by a fraction every time. That's what I'm going to have to do next. So I don't really want to do this even 3 times. So I'm going to go into my table. If your table's not already set up, you can do table, like the second window button. It needs to say ask right here. So I got there by using, do you see where it says TBL, SET at top of their table set? Okay, so you hit second, you hit the window button, it pulls this up, say ask, and then say auto. If it's set up like that, what it means is that you can go into your table, which you do by hitting second table or second graph, and you can delete X values and you can put in what you want. I'm going to put in the 3 that we said that we might have options of, which were 2/3, 7/15, and 2/5. You can see which one it has to be, right? It's the one that showed up as a 0. 7/15 is our culprit. That's the one I'm going to use with my synthetic division. So that's what we're doing next. Seven 15ths. So we're going to put the number 7/15 in the outside part of my synthetic division. Now, it sounds like it's really awful. It's actually going to work out cleaner than your third is thinking right now. So just bear with me. I have 15, -37, 44, and -14. So the first number 15 gets brought down. And we're all saying, hallelujah. 7/15 times 15 gives me a whole number. What number does it give me? 7, right? Those 15s cancel. What's -37 plus 7? 30, which also multiplies really nicely by 7/15. Oh, sorry, there's a negative there, yes. So if I take -30 times 7/15, what will I get? You can use your calculator if you want. It reduces wonderfully. Tiffany, I feel like you know what it is. What do you think it is? You're really close. -14. Yeah, because the sign. It is -14, but feel free to use your calculators. It's not a problem. How about 44 minus 14? 30. And if -30 times 7/15 was -14, what's 30 times 7/15? 14. And in fact, it better equal 0 at the end. Otherwise, we've got a problem because our calculator said it's supposed to, right? Yeah, and it does. So what does it mean? Well, it means I found one of the rational zeros. Agree? Or one of the zeros, period. It was a rational one. It means that x equals 7/15 is in fact a 0. And the other thing that happens on this one is that this piece that ends up at the end, which is 15x squared minus 30x plus 30, is actually pretty friendly. In particular, take a look and notice that they all divide by a single number. What number? 15. So I could factor a 15 out of this. Okay, so give me just a second. I'm going to shrink this. So if I take a 15 out of this, I have x squared minus 2x plus 2. I'm supposed to be setting that equal to 0. And what happened? It doesn't factor, but we already did it, right? We did it once before. We know the rest of the answers, right? So even if you just had to copy it down, right, on the additional problem, you're not having to do additional work. You've already done all the work for it. So these is from the previous problem. And I know that x is equal to 1 plus or minus I as my other two solutions. Any questions on that? It's a lot. I know it's a lot. Can you think of anything at the moment? Okay, our next section is a little easier. You guys ready to start it? Yeah, that part at the end is kind of stressful, especially on this